Спасибо большое. Okay, so we're gonna start our fourth lecture on modern dynamical systems. And we are still not on the most modern subject because we are still concentrated on the dynamical properties of the geodesic flow on the surfaces. So today, with respect to the previous attempts, in some sense, we are on the peak of dynamical interest because I'm going to discuss a few properties of our flow, including transitivity, ergodicity, as well as symbolic representation. But before we start, I would like to make a few announcements for the organizational part. First, please pay attention that in the our Google Classroom, I provided some possible topics for your presentations. So I recall you that one of the options to get the full mark for the course is to make a basis for it, given an oral presentation. So there are two first options that you can take. And the second important announcement is that the next lecture will be cancelled because we both are traveling. So the February 21st, there will be no lecture on dynamical systems. I also recall you that there is already one list of problems, and I'm going to provide probably today or tomorrow the second one. So it's a good moment to use this free time from the lecture to solve the exercises, unless you will be preparing your oral presentation. If you would like to take one of the topics, please send me an email or just comment in the Google Classroom itself, because in this way it will be visible for other participants that this topic is taken. Yes, later I will provide more. So if you don't like these ones, feel free to wait. There will be more. Anyway, we are still studying the geodesic flow. This is our protagonist for the next few days. Geodesic flow. I hope you remember the definition. It was based on the idea that first we defined the geodesic flow on the upper half plane, and then we projected it on our surface. So maybe I will recall briefly the definition. We started first with the flow on ash on the upper half plane, and it was an R action on the unit tangent bundle. S ash, which moves the tangent vector along the geodesic defined by its vector. And then maybe you remember that we made the identification between SH and PSL2R. So under this identification, the PSL2R action corresponds to a left multiplication, and the geodesic flow corresponded to a right multiplication by the following one parameter subgroup. We take diagonal matrices that looks like that. So this Vt of B is in one-to-one correspondence with GAT. And then we made a projection. So once we fix the group, that will be a fundamental group of our surface, we consider such a projection. So we got a projection of a unit tangent bundle, and then we projected the flow on the factor. So in the previous episodes of our TV series, we discussed that we found an invariant measure for our geodesic flow, and this measure was simply a Liouville measure. So we had dV that looked like d mu d theta. We had to assume that the hyperbolic area is finite for our surface. So this was a Liouville measure, and it was invariant under the action of the geodesic flow. And additionally, we proved the following theorem that was attributed to Dmitry Anosov, a great Russian mathematician. So actually the theorem statement is very simple. We just said that the geodesic flow is an Anosov flow. But then you need to understand what does it mean to be Anosov in this context. So there were a few things incorporated. I will write it up because today I'm gonna use it a lot. So the geodesic flow Vt is Anosov. Namely, there is a C infinite Vt invariant decomposition of the tangent bundle to Sm. And the decomposition looked like that. So we took a tangent bundle, and then we considered the tangent bundle to the tangent bundle. So be attentive, not be confused by the iterations of tangency. So there are three components. One is A0, then A plus, and then A minus. And you remember that they correspond to neutral, stable, unstable parts. So what does it mean? Here, the integral curves are simply the orbits of our flow. Curves, orbits of the flow. And here, the integral curves correspond to unit normal vector fields to the orocycles. Orthogonal to the orbits of Vt. And if you don't remember what does it mean to be an orocycle, please go back to the previous lecture because we discussed it. But morally, we deal with half circles, circles orthogonal to the line R, but we discussed what does it mean. And the most important point is that we can say much more about these people, E plus and E minus, because apparently what we do know is the rate of the divergence or convergence of the trajectories once we sit on the stable and unstable manifolds. So namely, we say that there is a positive constant C and lambda such that for any pair of points x1, x2 from the tangent bundle line on the same leaf of W plus or W minus, so let me write like that. What do we have is that we are able to measure the distance in the sense of W plus or minus between the images of these points. And we can evaluate it in the following way. And if we were in a stable part, we look to the future. And if we were in unstable part, we look to the past. So the formula is the same, but the real physical picture is opposite. Either you have a divergent or convergent situation. So either your orbits become closer and closer, or they become farther and farther. But morally, what is really important is simply that you can control these things in terms of this guy and the exponent here. So this theorem we proved on our previous lecture. I'm not going to repeat the proof, but now today I will show you why do we care about this kind of properties. Before we do that, let me state a few other important things. So I will need to introduce many different notations. Please be patient. You may be tired from them, but unfortunately I'm not able to prove one of my main things without it. So let me fix a point in the tangent bundle and then consider a stable manifold that contains this point. And then we consider a kind of a neighborhood of the point on the stable manifold. So we will consider all the points in this part such that the distance in terms of the stable manifold does not exceed some constant. So it's a kind of a neighborhood of the point if we look just on the stable manifold. If we are allowed to do this, we can also do a similar thing but in an unstable sense. So we fix a point W and we look at the unstable manifold. Containing W. And once we do this, we can fix a kind of a neighborhood. So there are all the points who live in the unstable neighborhood, such that the distance already in this unstable sense does not exceed some constant. The constant, however, can be the same. And now we may look at the following thing. Sx will be the set of points such that for some point that lived on the stable part, we fix a point, we consider guys from the neighborhood in a stable sense, and we consider those who enter it unstable part. So it's in some sense it's kind of intersection of two neighborhoods in both senses. If you want, you consider this is a condition in a vertical sense, and this is a condition on a horizontal sense, and you fix a point in three-dimensional space. You understand how it works. So this person will be called Sx. So it's a submanifold of dimension 2. And if we take delta that is small enough, we can assume that this Sx is transversal to the orbit of phi t. So local parameterization of our set is given by T u v, where T is responsible for the length of orbit through that for the flow that went through X. Dx plus is parameterized by the length measured over the stable leaf, and dw minus is parameterized by the length measured along the unstable leaf. So now, once we fixed all these notations, we are ready to state the theorem. That is also named after Anosov. It's called Anosov-Clausen lemma. So, theorem. We will refer to it as ACL. If we take a point in the tangent bundle and we assume that the point is such that the distance between x and phi t of x is not greater than epsilon, so if by chance we came back quite close to our x, and you remember that it's not so rare if you fix a positive neighborhood of x to be back to this positive neighborhood, because that's what Poincaré tells us in his Poincaré recurrence theorem. So if we do this, then in reality you will find a real periodic orbit just next to this one that was not necessarily strictly periodic. So there is an x0 in Sm such that the orbit of x0 is closed. Phi t prime of x0 is equal to x0 for some t prime. And we can say much more than that. We can also measure the distance between t and t prime and x and x0. Namely, we may say that there exists c, a constant, such that the distance between x0 and x is smaller than c times epsilon. And moreover, t prime minus t is also smaller than c times epsilon. So we don't need to wait too much, and we don't need to go too far from our special point to find the real periodic one. And apparently, we know even more that for t, which is between 0 and our t that was responsible for that, for our return, there exists some other constant c prime such that two orbits will not go too far away from each other. Namely, we have phi tx is estimated from above by c prime epsilon e minus minimum t minus t. So what exactly did we state in this Clausen lemma? We said that if we are going back to some neighborhood of our point, which is small enough, then we have a real periodic orbit nearby, We don't need to wait too much for this orbit to close, and moreover we can control the distance between these two orbits for the whole time that pass among 0 and the moment t when we return to the neighborhood. It's a very important lemma, not only because we're gonna use it a lot in the further applications, but in some sense it's a kind of original statement of a really serious theory which is called hyperbolic dynamics, because geodesic flow is not the only anosov flow in the world. There are other dynamical systems that satisfy a similar property. And then there is a theory about the closing lemmas and so-called shadowing orbits. So those orbits who share this property that we described here. And typically, people who deal with hyperbolic dynamical systems, they are trying to establish a similar result. So this is a kind of a baby illustration of what do specialists in hyperbolic dynamics do, how do they study their systems. So we are ready to prove this theorem. We will need all these notations, so I will send them upstairs, and we'll remove the definition of the geodesic flow. I hope it was already transparent. Maybe I will preserve this announcement. People need a reason for optimism, so we will keep it. Okay, so please keep in mind the notations from the upper blackboard, because otherwise it's easy to get lost. So we consider a point x that lived in Sx with some fixed delta. Then I claim that there is a T0 with the following properties. On the one hand, it's not too big. On the other hand, we can consider gamma an element of our fundamental group, such that if we go upstairs, here we're gonna use that it's not an abstract anosov flow, but it's a geodesic flow, so we understand it very well. So we can go upstairs to the upper half plane, do things there, and then project back. And so we claim that we have this property, and we consider the image of our Sx. So then we will have this, and then we have a flow that can be seen as a d gamma minus 1 phi wave t plus t0, such that it takes Sx to Sx. What I want to say is that here we know that we are going to some neighborhood of some point x, but I want to be back not only to general neighborhood, but to Sx itself, so to a very specific neighborhood. And I know how to construct it if I have phi t with this property. So that's what I do. This guy is an isometry. And thus we have that the distance between x and phi of x is smaller than c1 epsilon. And now we do the following thing. I will try to make a picture to make it a little bit more explicit. So we had x, and then you remember what we did here. So we had to introduce w and z, right? And there is x, there is d phi of x plus, and there is a d minus x. So I claim that I can find z here, such that phi of z will take us to d plus x. And then it's time to apply my Anosov theorem, because it was not by mistake that I wrote all these formulas here. So I want to apply this formula. I'm able to measure the distance between points if we apply the geodesic flow to them. So I claim that by this theorem, dw minus zx is smaller or not greater than c2 epsilon e minus t for some constant. So with these constants, they will appear permanently, but anyway, there will be a finite number of them, so we are always able to choose one that would satisfy all these conditions that we write up here. So this is our z, and we look at phi of z, and it will finish here, because that's what we required. So we will write here, sorry, it was d plus x, exactly, because x sit here, so it was phi of z. And now z, phi of z, and now we take x1 that will live here at the intersection of these two lines. What does it mean to be at the intersection of these two lines? It means that x1 belongs to d minus phi of z intersected with d plus of z. And so, thus, what does it mean when we apply the flow to this x1? It means that we necessarily finish in d plus phi of z. And then, once we have this info, we can apply our Anosov theorem once again. So we can measure the distance between phi of x1 and phi of z. And we know that due to Anosov property, since they sit on the leaf, we will have some constant multiplied on e minus t and epsilon. And then, what does it mean for us? Look here. So it means that if we may remove phi from here, we may say that then we can measure the distance between the points themselves. So we can say that this is smaller than some constant epsilon e minus t, and so on and so forth. So we can iterate this procedure and get every time closer and closer to our point. So this is phi of x, and this is d minus phi of x, and thus what do we have? That we can continue this procedure, so we can iterate this process. And every time we are getting closer to the original point. So every time the distance between the point and its image is getting smaller and smaller. So you get kind of an iterative process, right? And every time this constant is getting smaller and smaller, and so you see here you did not have e minus t. There was the distance between x and phi of x. Here you multiply it on e in a degree minus t. So if you repeat, you will get e in a degree minus 2t, and so on and so forth, right? So if you do it, at some point you will arrive to the point that did not move at all. That this distance is estimated by some decreasing sequence that tends to 0. So at some point as a limit you are supposed to have 0. So that's how you get a fixed point. And this is the first part of the statement we made. So the image of x0 is x0. Okay, great news. So we almost proved the point A. We still need just to control this time, that it was not too large, and then we can switch to the point B. So let's see why it should be true. We consider the gamma of x0, and it gives us phi t prime x0 for some t prime that was not too far from our time t. So we can be sure that the distance between x and x0 can be estimated by some constant multiplied by epsilon. And then we are also sure that just by our construction, this x0 that we built here, this one, should live in Sx. We never left Sx. So if we know it, then there is just one more step to arrive to the point B. Let's do it. Because that's how do you construct this x0. You always control these distances. So you control these parts, but you also control that you have you don't go farther than on the delta, on the stable and unstable leaves. And then if you switch to one point to another one, you have also this one. So you never exceed it. You always live inside of Sx. So it's something rather small. So for the same reason, what can we say? By construction, as I said, x0 belongs to Sx. So we take a w in dx plus such that x0 belongs to dw minus. And thus, there should be a constant that we can use to estimate the distance in both senses, in stable and unstable sense, between x and w and x0 and w. So this is under our control. And then we also know that this distance should not exceed c epsilon. So we can conclude that for some t1, such that t1 can be estimated, phi of t prime plus t1 x0 finishes in s phi t x. And so the distances, once again, we always apply the same statement from a Anosov theorem that we can control it. So it's smaller than this, and the same happens when you look at the unstable part. And so on. So you apply your Anosov theorem, and you see that the dw plus between phi tx and phi tw is smaller than some constant epsilon e minus t, and dw minus phi tw phi tx0 does not exceed c5 epsilon e t minus t. So then we conclude that the distance between the orbits of these 2 points, x and x0, should be estimated by some other constant, epsilon and e in a degree minus minimum of t minus t. So basically, the point C in the theorem of Anosov, together with some very basic understanding of the nature of the geodesic flow, allowed us to construct a sequence of points that every time was closer and closer to the notion of the periodic orbit. And so that's as a fixed point of the sequence, as a limit of the sequence, we constructed the periodic point. And then we checked, due to this property C, that we never property C is what is written here, that we never go too far away from the original point. And so we can control all the distances and get this conclusion. So that's the idea how this Anosov-Clausen lemma works, that you literally construct this periodic point by consequent iterations. And so we are ready to use it to prove a few properties of the geodesic flow in a pure dynamical sense. Let's do it. The first thing I would like to prove is that the geodesic flow necessarily has a dense orbit on SM. But before I do this, I will prove an abstract statement in the dynamical systems. So, lemma. Let us fix a dynamical system, a map on a metric space with no isolated points. So if there is a point such that the orbit of this point is dense, sorry, it's X, you're right. Then I claim that for any open U and V that are not empty, we may arrange things in a way that the image of one will intersect with the second one. So there exists K, it's an integer, such that the image of U will necessarily intersect V. You understand the point. So the fact that the orbit is dense means that it enters any open subset. But here I claim that even if you take the subset that is open but maybe not necessarily related directly to this X, it's not a neighborhood of X, for instance, still you can arrive to the fact that they have non-trivial intersection. Morally, we should not, basically I think you don't expect anything particular from this T. It should just have one dense orbit. Yeah, but the space should be such that you don't have isolated points, because if you have a space with isolated point, you can construct some ugly example. So it should be, it's called dynamically transitive or topologically transitive, your T. So let's prove first this observation, which is not obviously related to the geodesic flow itself, and then we will apply it to the geodesic flow. Because in order to prove its transitivity, I will prove this and not that. Okay. So each orbit of tk of X contains all but finitely many points of the orbit of X. So why does it look like? Because you look at the orbit, you need to remove those that corresponded to X, T of X, Tk minus 1 of X. But then all the further elements of your orbit of x, they will appear already in the orbit of tk of x. So you only remove a finite number of points. And we agreed that our metric space does not have isolated points. So that means that if orbit of x was dense, then necessarily the orbit of tk of x is also dense, because you need to correct only a finite number of points. So I can say that tk of x is also dense. But what does it mean to be dense? It means that you enter any open subset that you can imagine. So more or less it means that if your U is non-empty, then there exists K such that Tk of x is in U, and also that there exists M which is not smaller than K, such that Tm of x is in V, because both of them are open. So since we have everywhere dense orbits, we should enter both of them. But now, since we assume that m is not smaller than k, I can consider T m minus k of tk of x. This was a person living in U. So this person, after T m minus k iterations, entered V. And so we are done. We checked that the property to be dense implied that we necessarily entered any other V, right? Great. So this was the first lemma. Now I want to prove something kind of in the opposite direction. And in order to do so, I will recall you what Baire category theorem states. I think you heard about it in topology. So let us do it. Da. I think we never used it. No, because what we really wanted is just to have a dense orbit. It's quite a strong requirement, however, because not every map. No, but you never use it. You just use density everywhere. So I recall you what Baire category theorem is. We have a complete metric space. And we have a collection of open dense subsets of X. So then the intersection of all our UK is also dense in X. Why it should be true? Let's think about it. So we consider some non-empty open subspace. In order to check that something is dense, we need to check that we necessarily enter this non-empty open subset by elements of our set. So it's we want to show that there exists X in V such that X enters the UK for all k, because X should be a member of the intersection of these people. So let's start from the beginning, from U1. U1 is open and dense. So there should be X1 that lives at the intersection between U1 and V, and such that if we consider a ball of a radius R1, then this ball lives properly in this intersection. Because we have the intersection of two open sets, so we should be open, so we should have a neighborhood that enters it properly, right? And R1 is not too big, so we can assume that R1 is between 0 and 1. It's a closed ball, we can think. Because we have some open subset that enters due to the fact that they two are open, but then you can say that inside of the open guy you may find a closed one, maybe smaller one, but still who lives properly. So we can iterate this procedure for every U key. And every time we can assume that this R is smaller. The corresponding radius is smaller than the previous one. So we will assume that Rk is between 1 over k and 0. And so we got a system of balls that looks like that. That bxk is a part of bxk minus 1, rk minus 1. It's an open ball intersected with uk. So we built a Cauchy sequence. But I was not stupid. I asked that my space is complete, so I can be sure that Cauchy sequence behaves very well. So there should be a limit. It's not a dynamical theorem, but I will use it to make the complement to this statement. So let me do so. Hope you remember what Anosov-Clausen lemma is about now. So lemma 2 is called Birkhoff transitivity theorem. So we have dynamical system, and we will assume that this space is very nice one. By the very nice, I mean that I want it to be separable, and I don't want it to have isolated points, and it also should be complete, because otherwise Baire will not help me, and metric. So a lot of requirements. So the existence of a dense orbit then is equivalent to the fact that for any non-empty u and v, the tk of u intersected with v is non-empty. Assume that, okay, they are open. Okay, in one direction we know that it's true. We checked it already. even with less strict conditions on the metric space. So lemma 1 implies that if we are given a dense orbit, then we are lucky people. We don't need to care about this. It necessarily holds. So now it's our responsibility to check the opposite direction. That if this condition is satisfied, it's enough to be sure that it has a dense orbit. So X is separable space. Then we can cover it. So there is a countable collection of open sets UK. K, it's countable, so we can enumerate them. So they form a basis for a topology. So a point has a dense orbit when? If we enter any open subset, right? But what does it mean to enter any open subset if we know that we have a basis for the topology? Then we can consider any open subset. We can rebuild them with this UK. So it means that it's enough to be sure that we enter any UK. That's what we will do. So for any k, there exists a non-negative integer m such that Tm of x enters UK. Good news, so now we only need to check what happens if we look at the UK. And I suggest us to look at the following point, so the following set. We will call it set of points with dense orbits. So, set of points with dense orbits. So, dense orbits. They are those who enter all the UK, right? Because we agreed that in order to be dense, we need to enter UK. So we have to consider the intersections of the union of the pre-images of UK. Right? So we need to enter UK at some point. In order to do it, we need to if we need to enter at some point, we consider all the pre-images, we consider their union, and then we need to enter all the UK, so we intersect them, right? Then we need to check that if we have this condition, let's mark it by the star. If we do that, then I claim that all these people are necessarily dense. So I claim that this implies that this union is itself dense. Because for any two open parts, so it means that including if we take UKs as U and V. So let me add here that I want T to be continuous. At this moment I need it indeed. I forgot, sorry. I will apply it as the condition, because there we only played with the density, but here we need something from T as well. And namely, we want that this thing is also open. And we can guarantee that it's open only if we have continuity of T. So we have a dense and open thing, and there is a bear who wants to help us. He knows that we have open dense subsets, And he says that then you can intersect them, and it will be a dense set. So the bear tells us that this set that we constructed here is necessarily dense set. But if somebody is dense, then we can be sure that this dense person is at least non-empty. It's very hard to be empty and dense. So this is more or less impossible, and then it means that D is non-empty. But that's exactly what we want. That if it's non-empty, then we can be sure that there is a point such that its orbit is dense. So, going back to the original problem we were interested in, we can be sure that we can check this star property instead of the property to have a dense orbit. So for the geodesic flow, our goal is to prove its transitivity. So we're gonna check that the star property is satisfied. That's our plan. Let's execute it. So theorem. Let's say that we have a surface that we see as a factor of a upper half space with respect to the action of the Fuchsian group. And we want that the hyperbolic area of this surface is finite. Then I claim that the geodesic flow is topologically transitive. So that it is, in other words, has a dense orbit. We will prove this theorem using our observations that we made there. So we need to check that there exists a T such that the phi T of U intersected with V is not empty. We agreed that that's enough to be sure that we have a dense orbit. So we call Anosov to help us, and he comes with his closing lemma. He says that he can build us a periodic orbit. Since Poincaré already guaranteed us that if we take a neighborhood of a positive measure, that's why we added this thing, because we want to have Liouville measures there. So if we have a thing of a positive measure, then we necessarily will be back to this neighborhood almost always. Then we are in the situation when we can apply Anosov closing lemma, both for U and for V. So Anosov provides us two different periodic points, one living in U and one living in V. And we have to fix them. So we say that this is U, this is V, and they are periodic. That's great. So we may consider also the lifts of these points, and we will also call them U and V. I hope it will not provide any confusion. Okay, lucky us. Then we can specify a bit what kind of points they are. So Cu and Cv, they will be two geodesics. We lifted, so they correspond to our points. So now we can assume that Cu minus infinity do not coincide with Cv infinity. If it's not true, if they coincide for some unclear reasons, then we can just apply whatever isometry. It will not spoil the fact that they're geodesics, but so we can replace Cu, otherwise replace Cu by some gamma Cu, where gamma is in gamma. So now let's apply ICL one more time. What does it tell us? So Anosov-Clausen lemma, the B part of it, guarantees that for any t, there exists Gu of t and Gv of t such that d of Cu Gu of t Ct is smaller than the exponent of minus t. So t goes to minus infinity, and a similar thing with v. Gv of t c dot t minus t goes to infinity. So now these two people, these geodesics, they can be projected to the closed geodesics on the surface. So in reality, what we have is that once we project, is that there exists T1 and T2 such that the projection of C1 dot to Sm is in U, and a similar thing is that projection of C2 T is in V. You can say that it's Cu and Cv. And thus we arrived to the statement we wanted. So morally, what we did, we applied twice Anosov-Clausen lemma. First, we used it to find some nice points that we will use to check everything, and they were periodic points, so we knew that we are back to the same point. And then we used it to control the distance between the corresponding geodesics and thus between the corresponding flows. It's a geodesic So you consider geodesic C. You're right. Maybe I forgot to say it. So you built it like that. C is a geodesics, and you want that at infinity it coincides with V, and in minus infinity it coincides with Cu. So we construct artificially this thing. We assume that these 2 points are different, so such that we identified 2 different points, and we consider the geodesic that passes through these 2 points. And then we measure the distance between these geodesics and our guys, and we check that we can control it due to a nocive closing lemma. And then it was enough to be sure that we will enter both of these sets. And moreover, we proved actually much more, because we did not prove just the existence of the dense orbit. We checked that these dense orbits are those that are periodic. So in particular, we checked that periodic orbits are dense. Because our proof was constructive. We used the nocive closing lemma to build the periodic points, and then we checked that these periodic points are those that are dense, right? So we checked the density of the periodic points. And this is a very nice observation that slightly recalls us our favorite dynamical system, the one that we discussed at our first lecture, that we understand the best. I mean the rotation on the circle. Because, you know, the rotation on the circle has periodic points only if it's a rotation on the rational angle, right? But at the same time, the rational numbers are dense in the set of all numbers, all real numbers. So we have exactly the situation when periodic points are dense. And here you see it's a rather similar case. We will see the second half of our lecture that it's not just a coincidence. So now we are ready to prove probably our most important result for today. Namely, I want you to check the ergodicity of Liouville measure for the geodesic flow. And I will try to explain it in the following way. I state the theorem, and then the proof is based on a very classical observation named after Hopf. So it's called Hopf argument. I will explain you how the Hopf argument works, not for the geodesic flow first, but for total automorphisms, these guys that we studied at the first lecture, when we took a matrix 2 by 2 with integer coefficients, you remember, and applied it and checked what happens. So I will first explain you how the Hopf argument works for the total automorphisms, and then we will reproduce this idea for the geodesic flow on the surface. So, theorem. The Liouville measure dV on Sm is ergodic under the geodesic flow. Before we do that, I need to speak a little bit about ergodicity. The course is not about ergodic theory. We have a different course on this subject. But definitely we need to understand at least some very basic things on this notion. So I need to comment on a few facts that concern this notion. Let us fix the probability space and consider a measure preserving transformation we consider a function and say that the function simply acts on x and take us to R. I will say that this function is t invariant if the composition of f and t is f almost everywhere. So it means on a set of measure 1. And you know the definition of ergodicity that we introduced at the very first lecture, saying that all the invariant measures are those who have full or zero measure. All the invariant sets. So there is an alternative definition. We say that a measure preserving transformation T is ergodic if any T invariant F from the set L1 is constant. L1 can be replaced by LP for any P between 1 and infinity. So it's morally quite understandable feature, because if you have a T invariant function, you may think about it in the following way, that if you have an invariant set, the set that is invariant under the action of your map, then you may consider the characteristic function of this set, right? And then if you consider this, it should be T invariant if it's a characteristic function of a T invariant set, right? So then you may think that if it's T invariant, then it should be constant. It exactly means that this characteristic function should be constant almost everywhere. It means that your set either occupied almost the whole space, or it vanishes everywhere, almost everywhere. So morally, we understand that these two things are equivalent. The definition we used at the first lecture and the current definition. I will stick to this one for today because it's easier to check. There is another way to express the same thing that recalls much more the constructions you saw in probability theory while studying independent events. So there is a proposition. We say that T is ergodic if and only if lim 1 over n of the following sum. We measure t minus ia intersected with b. Here we sum up from 0 to n minus 1. So this guy should coincide with the product of measure a and b for any measurable sets a and b. Why did I tell you that we have something that looks pretty much as a definition of independent events and probability? Because you see here we have a product. These two measures, we consider their product. But that's exactly what happens when you try to compute the probability of the event, which is an intersection of two independent events. That its probability is a product of two probabilities. So here you want to say that in average the preimages of any events are asymptotically independent from the other event on average. Not necessarily literally, but for any iteration, but asymptotically, when you consider averaging along the orbit, you get this independence. So that's the physical interpretation of ergodicity. And the key theorem in ergodic theory is the one due to Birkhoff. It is the theorem I suggested you as a possible topic for the presentation. So it's the following thing, that if we have a measure preserving transformation, then for any f from L1 and almost every x, the limit (1 over n f ti of x is f star x, where f star is a function in L1. Okay, here from a function in L1, which is t invariant. And this is true for any f, for any t, sorry. It should not be ergodic. It's enough to say that it's measure preserving. Then we already can average like that. But if we add ergodicity, actually we have much more. Namely, we know that it doesn't matter how exactly to average, on the observables or on time. So it's like, if t is ergodic, f prime, f star is the result of the integration of our f. So in ergodic case, time average converge to the space average. Ergodicity means that averaging observables along orbits gives us as little information as possible. So there is no additional information. It doesn't matter how do you average, on the time or on space. I'm not going to prove it because I asked one of you to take it as a presentation topic. So please check the links to understand how it could be done in the Google Classroom. But at the same time, in order to tease you and convince that one of you necessarily needs to speak about it, I will show how we will apply it. So we will use this theorem to prove our ergodicity of the geodesic flow. I think we are exactly at the point when we can make a short break. It's not prime, sorry, it's I. Because here I is the one that you use to average. It's the index here. Okay, so we make a short break. I think it's the moment to do so. Why is it so noisy? Что-то шумно. Почему? So let us restart the lecture, and we stopped on the following moment. We stated the theorem, and then we made some preparatory work. I skipped the most meaningful part, namely I'm not proving the statements. I think that this one you can prove by yourself, and this one I hope somebody will tell us as one of the oral presentation part. Otherwise, at least one can check the links that I provided for the oral presentation to recover the proof. So I want now to apply it to get the proof, to explain you what the Hopf argument is. And we will leave for a moment the geodesic flow and illustrate the ideas on the maybe a little bit more explicit object, the total automorphism. So the theorem is the following. We take a matrix that lives in SL2Z. It's a hyperbolic matrix. And then T defined by TV is AV modulus 1 is ergodic with respect to the Lebesgue measure on our two-dimensional torus. So the idea is based on this observation that we discussed here. Namely, we want to check that the invariant functions are constant, and we will check that it's true using the decomposition into stable and unstable components. Because as you probably remember, at the first lecture, we already talked about kind of Anosov property for the total automorphism. So maybe I should leave some trace of this statement. So the idea is as follows. We will look at the Birkhoff limits and try to check that they are constant almost always on the leaves. Then we will try to apply Fubini's theorem, because you understand what Fubini does. Maybe you remember from your measure theory course that if you can say something, we will specify what exactly. You have say two-dimensional picture, and you can say something about x component and y component. Fubini gives you a chance to say something about the two-parameter function, which depends on x and y, roughly. So that's what we are trying to do. We want to look at the stable leaves, say something, unstable leaves, say something, and then glue it together, because we have this decomposition on the integral curves of the dynamical system, on the orbits, stable part, unstable parts. So we will try to glue the result from our estimations that we get on stable and unstable parts separately by the extension of Fubini theorem. So that's our plan. Let's try to execute it. So we take f, which is a continuous function on the torus, and we take y, which is a set of full measure full Lebesgue measure such that for any y, a limb of this thing is equal to y. So here we said that for almost all x we have such a limit. So now we consider the set of points for which indeed this statement holds. So it's a set of a full measure, but it's not necessarily any point. This is a key property of ergodic theory, that you never are able to say something about any point. You very often can state something about almost any. And you understand the very delicate difference. Because if I give you some particular point, ergodic theory tells you nothing about it. Because it doesn't know what's going on in a particular point. It only knows what happens to a typical one. So we will call it regular or Birkhoff regular. And we fix a stable leaf. It's a stable leaf. And we consider two distinct points, y and z, such that they live in this stable leaf and they are regular. Then we know that the limit between the members of their orbits is 0, because we have this Anosov style estimation, and because we know that it's a continuous function. So, but now we can this comes from the Anosov property, because we live on a stable leaf. So when we iterate it for a long time, we have e in the power minus te, and so it goes to infinity, right? So now you may think that you can rewrite it also using this property. We use this, but we have not used regularity yet. So now it's time to use regularity. So it's greater or equal than if we will consider such a limit separately. So but then we also know that this regular property holds. So we can apply that. And in order to do so, we can say that we may replace these two sums, saying that it's smaller than epsilon, iterated many times. And thus, we have a property that this should be approximately epsilon. And therefore, we know that this thing implies that f star y is equal to f star z. Was it clear what I said? That we have this distance equal to 0. F is measure preserving. So it means that if you consider the distance between f of ti and f of tiy and f of tiz, then we can replace it and say that there are 2 points ti y and ti z that are very close to each other starting from some moment, right? So f is a continuous function. And therefore, we know that starting from some moment, this difference between f and 2 points that are very close should be also very small. So only a finite number of them, that's why we separated it into 2 parts. This n, capital N, corresponded to the moment from which we can assume that this distance is smaller than epsilon. Because after that moment, we can be sure that also the difference in the values of this f is something that we are able to control. So we only need to control a very few first steps. But since we have 1 over n here and the finite number, sorry, it should be 1, and the finite number of elements here, then it's something bounded, and it's something where n goes to infinity. So we can be sure that this guy is very small, and this is very small because f is continuous function, and we have this property. So necessarily we get something that allows us to estimate it, and we can be sure that they coincide. Do you agree? Okay. Now it's moment when we can try to apply. This was the first step, and we are going to make the second one. We want to apply Fubini's theorem. So we consider a part which is measurable. It's a 2-dimensional picture. And there ESX, these stable people. So the measure of z can be seen as follows, that you consider the integral over this stable part of the characteristic function, and then you integrate from 0 to 1. So we assume that we have a set of Birkhoff regular points. And thus, on the one hand, we know due to Birkhoff ergodic theorem that the measure of this set is equal to 1. But at the same time, we can also represent it in this way. So we can say that it's an integral from 0 to 1, integral over the stable leaves of the characteristic function dy dx. But this can be replaced by saying that we integrate from 0 to 1, from minus infinity to plus infinity, x, y intersection ESX, y dy dx. And you understand what happened, because we simply the same thing to integrate over this guy, this person. This is a capital Y, maybe I'm not very accurate. So instead we consider the intersection, and then we integrate from minus infinity to plus infinity. The same thing. So now we say that apparently the inner integral, what is it, this guy? For the integral from minus infinity to plus infinity of the characteristic function dy. It's nothing else but the measure of this set that we characterize by this function. So we can say that this person is a measure of ESX intersected with y. And so now we consider the measure of this along the leaf ESX. So it's non-negative necessarily, and it's necessarily bounded above, at least by 1. So what we have is that there is some function which is equal to 1, and at the same time it's bounded. So we can, you understand? So we know that it's equal to 1, but this function itself cannot be greater than 1. It's a characteristic function. So if we integrate it, then we cannot get something greater than 1. So we should always have 1. So this characteristic function should be almost always equal to 1, because if it's 0 too often, we will get too small. So that means that it should be equal to 1. Now we are almost done, and we only need to make the very last step. So what we checked already, we want to check that all the constants are equal. So I recall you what we are looking for. We want to prove ergodicity. So Birkhoff told us that this limit exists. I think I have not erased yet. Yes, Birkhoff said that this limit exists. We checked that when we sit on one leaf, it's stable, the value of this function. Then we used Fubini to extend it, this statement. Now we need to check that all the constants we get in this way. So we checked that this integral is equal to f star along the leaf. And now we need to check that all the constants we get in this way, they all are equal. So basically what confuses us is the following thing. We need to consider y intersection with as x, and then we take another point and consider the intersection of the corresponding space with this point. So we have to check that if we translate it along any unstable line, then we necessarily intersect the set y intersected with E unstable z in a set of full measure. And then, therefore, what do we need? We must therefore get that z that lives here, let's say z that lives here, and w that lives here, such that they both sit here for some p. And then we have the same function here and here. So we can be sure that our f star is constant almost everywhere on T2. Do you understand what's going on? So we checked what's going on through one leaf, then we extended it using Fubini, then we checked that indeed this function, we want to prove that all these functions are constant. So we checked that they coincide if we had two different things, one associated with one stable leaf, another one associated with another one, then they necessarily coincide, these f stars. And so the very last observation is the following thing. So step 4, it's the very last technical detail. So we check the following lemma. We say that we have a measure preserving transformation. Of a probability space. If D is dense subset of L2 x mu such that the Birkhoff limit f star is constant almost everywhere for any f from D, then T is ergodic. So we claim that there is a way to make a Birkhoff theorem slightly weaker, the condition there. The conclusion is on the same level of strictness. So we claim that we may check it just for a dense subset of all functions, and this will be enough for us. And if that is true, then we can come back to our statement, see that actually the set of continuous function is dense in L2, and therefore we are done. This I'm not going to prove. It's not hard, but you need to know the proof of Birkhoff-ergodic theorem for that. So I leave it for the next time when we're going to discuss this proof. So, but I think you morally understand what happened. We checked everything for the continuous functions. Indeed, we used that it's continuous. You remember on the very first estimation when we said that we can split the sum into two parts, and the first part was just finite, and the second part was exactly very small because of continuity of f. So we used it, we checked it for continuous function, and that was enough to say that it's true in general. So now I fix my shoes and I will continue with a more formal presentation of the same argument for the geodesic flow. Шнурки развязались. Okay. So we prove the statement about ergodicity of the geodesic flow, and basically we try to reproduce the same strategy that we discussed now. So first we want to apply Anosov theorem to get some estimations to check what happens when we sit on the stable or unstable leaf, to prove that indeed all the invariant functions along these leaves are constant. Then we use Fubini to extend it to a two-dimensional set instead of one-dimensional, and then we check that what we did was enough. So let's say that we introduce a stable relation. So we have a function that acts on our surface, and we have a stable equivalence relation. X is equivalent to y if the distance between their iterations goes to 0. So then WS is a stable equivalent class due to the Anosov property of the flow. And if we consider invertible functions, then in a similar way we can define also unstable class. we will recall it. Okay, this is WS and this is WU. So the first step is to show that Birkhoff averages for continuous functions are constant along stable and unstable equivalent classes. So how it could be done? We consider a function, integrable one. And we consider f bar, which is a lim sup of this. And if phi is continuous, then we can be sure that for any x in M and x prime that lives in a stable class of x, the lim of the distance between fn of x and phi fn of x prime, this is equal to 0. So that means that f of x and f bar of x prime then coincide. So if the limit of phi bar exists for x, then it exists and it's constant on the corresponding stable leaf. So constant on stable leaf. The argument is exactly the same as we already constructed there before, because you can estimate this thing using the fact that there is an Anosov property and continuity of function. Now we can say that projection is continuous, so we can project this thing. It's equal up to the set of modulus 0 to the projection of it to f invariant function in L2. And now continuous functions are dense in L2, so the ergodicity of f is equivalent to the fact that the projection of any continuous function is trivial. But it is the same thing as to say that this f is constant almost everywhere. Now we need to check that we can apply Fubini's theorem, and it follows from the fact that we consider f invariant functions and f minus 1 invariant functions, and see that these two sets coincide almost everywhere. So if we have these guys who are constant along stable leaves, and these that are constant along unstable leaves, they coincide almost everywhere. So here we invite Fubini, and Fubini's theorem implies the result. Now let us write the same thing slightly more formally to be sure that we believe in every internal step. So we consider f plus of x the ergodic average is constant. This is what we want to show, that it's constant almost everywhere for every function f in L1. It is sufficient to check it only for continuous function, as we discussed, because they are dense in L1. We even can add the requirement that we have a compact support. Then the existence of such a limit follows from Birkhoff ergodic theorem. Birkhoff ergodic theorem, existence. So we know that it exists. We now need to check that it's a constant. So we first check that it's a constant on stable leaves. How do we check it? We fix a point for which this limit exists, because, okay, we always have a situation when we know that something holds, but almost everywhere and not necessarily everywhere. So we take a point for which we know that it exists. Now we consider the stable manifold containing this point, and we check that for any q in this stable manifold it also exists. Because what can we say? We consider f phi t of pi minus f phi t of q, and we say that starting from some moment this thing should be smaller than epsilon for sufficiently large t. And then we apply continuity as before, plus the fact that we have a loss of property, and we conclude that necessarily the difference between two integrals is smaller than this epsilon. And moreover, this limit does not depend on q. So since the existence and the value of the limit is phi t invariant, then we can be sure that along a weak stable manifold, the integral manifold, which is done by a0 plus a plus, so here we are happy people. Then we do a similar thing with unstable manifold, and we have a similar situation. It also exists. But then it exists not only on unstable manifold itself, but also on a weak unstable manifold. But on a zero, it should coincide. So then it coincides into these situations, and then we apply Fubini, and we reach the result we are interested in. So that's basically the Hopf argument as it is. Hope it was rather transparent for you. And I have only one remaining plot for today, which is morally very different from what we discussed up to now, because I want to talk a little bit about the connection between the dynamics of the geodesic flow and symbolic dynamics. So I erase what we had, give a very small pause to you to recover. So in our course, we use geodesic flow as a kind of a toy example of a dynamical system, and we examine it from different points of view and introduce different tools to study it, such that these tools can be applied also in a much more general context, but we get familiar with them playing with the geodesic flow on surface. And we already touched a bit some general dynamical properties and ergodicity, but we have not discussed much what's going on with the symbolic description. Maybe you remember that at the first lecture we discussed the fact that many famous dynamical systems are related with each other, and this relation can be expressed in terms of conjugation. And for example, we discovered that there is a connection between the Gauss map and the general continued fractions and the automorphisms of the circle. So today I will try to convince you informally that actually the geodesic flow on surface, especially on a particular surface which is called the modular surface, is nothing else but the continued fractions that you are very familiar with. Before I proceed, I make a small teaser for the topic of the presentations that I gave to you. One was this Birkhoff ergodic theorem that we discussed so much today, but another one was about Dirichlet regions. Dirichlet regions are particular examples of the fundamental regions that look nicer than others, for the fundamental regions for the Fuchsian groups. And so one way in which we can think about the symbolic coding of the geodesic flow on surfaces is the idea to look at the fundamental regions, for example, at the Dirichlet regions. They look a little bit like hyperbolic polygons, and then we can try to apply the approach that people would use while studying billiards and rational polygons in order to get their symbolic description. Mainly you can code all the edges of your fundamental domain, and you give different letters for each edge, and then you can try to describe your orbit, saying which edge was touched at the current moment. And so you get, if your fundamental domain is nice enough, and it's exactly the case of the Dirichlet region, you get a presentation in some words, and the dynamical system you have will be a shift, and you may describe it in terms of substitutions and so on. This is one approach, and this is why, for example, people do care about Dirichlet regions, because it gives us a rather nice way to describe the symbolic presentation. But I will talk about a slightly different one way, because I want you to read about Dirichlet presentations by yourself. So this is due to Caroline Series, I think. And if you read in French, there is a very cool paper by Pierre Arnoux that gives a more elementary presentation of her argument. So it's something on the symbolic coding of the geodesic flow. The idea is the following. We look at the modular surface. So the modular surface is that you take SL2R and you factorize it on the action of SL2Z. So this is our surface. And as you know, the geodesic flow is somebody who is determined by the action of such a 1 per meter subgroup of diagonal matrices. This you can also see in a kind of more geometric way as a space of lattices in R2. So what I'm going to do now, I'm going to provide a nice fundamental region for this action. This fundamental region will be formed by rectangles, but they will not be just rectangles that really share the edge, but it will be more like two rectangles of different size that are located more or less like that toward each other. And so when I apply this procedure to them, what happens is that, as usual, you kind of do in one direction, you do the contraction, and in one direction you do the expansion. And so it allows me to see this action, to associate it with a continuous fraction. Continued fraction. This I recall you what we are talking about, so we have things like that. And AI is positive. So you can consider two maps from 0, 1 to n, natural numbers. One takes an integer part of 1 over x, and another map, it's from 0, 1 to 0, 1, takes a non-integer part of 1 over x. So this thing, this t that I defined here, can be extended. You can get a two-dimensional extension of it. And it will act on a special set which we denote by sigma. Sigma is described like that. You take x from 0 to 1, but if x is smaller than 1/2, then you say that your y should live between 1 plus x and 0, and otherwise it should live, it should be the complement. So what I say is that I can define it like that. I have now a couple of points, and I map them to what t does to x, and x minus x square y when x is non-zero, and if x is 0, then I just take my points to 0, 0, and I claim that if I'm not here, then my t wave is a bijective map. And if I consider the vertical segments, so those for which x is equal to is a constant, then necessarily I will go to the vertical segment as well. And so what it will do is that, maybe I make a picture, it will be easier to follow me. So I will have a picture like that. I have stripes. The stripes is identified by the fact that it's between 1 over n plus 1 and 1 over n for x. And then I also run to the same part of the coordinate set, but I will do a different stripes. So this one will go to this one, and then there is 2, it goes to these 2. So those who were kind of defined a vertical division, now it identifies a horizontal one. So the rectangle, formally speaking, the rectangle that was between n plus 1 x and y between 1 over 1 plus x and 0, it's taken to x, which is between 0 and 1 simply, and y between 1 n plus x and 1 n plus 1 plus x. So we do also half rotation, and right side switches with left side and top switches with bottom. So what I claim, why do we care about all this? I claim that the first return map to the geodesic of the geodesic flow is exactly described by my t wave. So I claim that if we deal with the geodesic flow on the modular surface, the first return map of this guy can be described by basically a continued fraction with some addition, because we are in a two-dimensional space. So these two maps are, if you want, they are conjugated. And now I will try to explain why it should be the case. We will think a little bit how the geodesic flow on a modular surface look like, because we know how the geodesic flow looks like, right? But if it's a modular surface, we in reality know much more, because we can draw a fundamental domain, we can write up the matrices, so we can play a little bit with it to make it more explicit. But I hope you understand the statement, right? I claim that the first T wave that we constructed here, this guy, it's a first return map of the geodesic flow on M, where M is my modular surface. So let us try to prove it, to explain it at least. So we consider the modular surface. We can think about the fundamental domain in the following way, that you look at such a stripe, and so you get this part as a fundamental domain of the geodesic action, geodesic flow action. So this is my geodesic flow, and we know how the tangent bundle looks like. In case of PSL to Z, PSL to R, P does not matter. You can add it or remove it, it doesn't matter. So you can think about the flow in different terms. You take a matrix. Sorry, it's better to write it like that. You take a matrix, and you consider two basic vectors. So you can think that they identify the basis in R2, and they give you a part of volume 1. So if we multiply this matrix by some other matrix on the right, we will have a standard action on R2 by the transparent, by the MT, the transparent matrix. So in a similar way, you can also describe what happens if you switch to Poincaré disk model. So this base will give you two complex numbers, and so you may think that you associate the ratio of two complex numbers with each couple. And this map is invariant under isometries. So if you take SL to Z matrix and multiply it on E1, E2, you will get another basis for the same lattice. And in order to describe the geodesic flow, we fix the coordinate base in the space of lattice. We consider some point, and we consider the neighborhood of this point. This is a point X, and we consider Hx, which is x minus 1, x plus 1. And so then we can think that we will consider a vertical ray starting from X in our parameter space. So it should intersect at least one horizontal horizontal interval from our lattice. Sorry. Otherwise, no, it's impossible that we don't have this intersection. So either we arrive to the vertex of the lattice, or either we have intersection uh, that is not at the vertex, so it means that you have a rationally independent x coordinates for the vertices of your lattice. So in this case, you can come in the lattice arbitrarily close to some to this vertical ring. So we intersect it again, and we say that this is a set that we call HY. So the intersection point, we can assume that it was to the left to the point Y. So in this case, we say that x plus e multiplied by c is y minus a. And we consider Vx, it's a part of this vertical ray, x plus ic. So then we extend to the right all the horizontal intervals in that way that their new rightmost points, it's a point of intersection with the interval. So we extend them up to the moment when they meet this vertical interval. And so for each Vx like that, there exists Hz, z plus b. After extension, we arrive to x plus id. And we continue to do that. And so we get the, you understand that this A, B, C, D are those that are coordinates here, that are coordinates in this matrix. So we built a kind of a fundamental domain for our lattice formed by two, it's AD, BC, by two rectangles like that. This provides us. So once we have such a fundamental domain, then we start to act by SL2Z on this fundamental domain and see what happens. And so what does the geodesic flow does to us, to these four numbers, GT, A, B, C, D? It gives us ET over 2A, ET2 over 2B, E minus T over 2C, E minus T over 2D. But if T is big, these two people may exceed 1, and so we will need to consider the first return map, the moment where we have to glue the sides of the corresponding fundamental domain. So the flow can leave the fundamental domain, and we will need to add the jump. You understand? What happens? It's like when you consider, for instance, the billiard flow, you touch this part, and then you jump here. So here you do a similar thing. You consider one fundamental domain, and you consider the first return map to this fundamental domain for your geodesic flow. And since T can be big, and you multiplied E, A and B on these two guys, then it means that if you don't want to leave it, you need to jump. So you need to understand how this jump will look like, and once you understand this, you know how the first return map look like, and you can compare it with these fractions that I presented. So that's our plan. That's what we want to do. And in order to do it, we say that exactly we get a precise description. So we consider a few subsets of this four-dimensional space. Because we act by AC minus BD. It's an inverse matrix. So then we do a sigma 1. It's once again the four numbers, similar way, but a different ordering. So they are the faces of our three-dimensional fundamental domain. Here C, in the last one, C is equal to 0. So it's simply AD equal to 1. So the flow can leave the fundamental domain, as we said. Now let's see, we can parameterize sigma 0 by ABC, because we can express D. It's enough to know 3 parameters, we don't need the fourth one. So we can see it as a part of R3. So we can analyze how it looks in R3, and it has 5 faces. Some are very elementary. When B is 0, C is 0, C is 1 over A plus B, A is 1, and B is 1. So here the flow enters, and here the flow leaves. We will call it sigma 0 and lambda 0. So sigma 0, since A is constant, can be parameterized by B and C. B goes from 0 to 1, maybe 0 is included, and C goes from 0 to 1 over B plus 1. And in a similar way, here B is fixed, so we need only 2 parameters. A is greater than 1, C is between 0 and 1 over A plus 1. So in a similar way, you can parameterize this guy as well. And now what we state formally is the following proposition. So the first return map T wave of the geodesic flow on sigma wave, which is formed by sigma 0 and sigma 1, is a 2 cover of T that we identified before. I add here epsilon, just meaning epsilon takes values either 0 or 1, because we need to switch between these 2 cases. So it does not influence the appearance of the function. So it means that we switch. If we were at sigma 0, we switch to sigma 1. If we are at sigma 1, we switch to sigma 0. So the proof is very strict. You just do this. You consider this lambda 0 that I defined there, and I identify it with sigma 1. So we have a pair. We can easily interpret it in terms of the fundamental domain, and we can say that we do this. And the identification is done by the multiplication on the following matrix. So once I try to compute the first return map on sigma 0, I have that x and y under the time, which is equal minus 2 log x, should go on 1 over x, xy. And since we cannot exceed 1, it's the same thing as to say that I take a fractional part here and replace it by this thing. So this already lives in sigma 1, and the symmetric calculation gives me the opposite. So basically it means that my geodesic flow is associated to the coding given by the continued fraction, and my geodesic flow can be seen as a special flow with a return time given by minus log t. I want you to remember this construction, because when we will study Teichmüller dynamics, we will see a morally very similar thing that will happen to Teichmüller flow. So I hope it was relatively understandable what we did now. So we found out some kind of natural symbolic dynamics, the description for our flow, and we presented this flow as a first return map to some particular fundamental domain. And once we chose a smart fundamental domain, we saw that our flow is nothing else but a continued fraction. That was our idea. So I think I stop here for today. The next lecture is cancelled. And once we are back, we will try to apply our knowledge to some generalization, namely to the analog of the geodesic flow in a moduli space, to the Teichmüller dynamics. See you within 2 weeks. Thank you for your attention.